Have you ever wondered how your phone just knows how to tune into a radio station with perfect accuracy, or how a piece of lab equipment can create a flawless, high-frequency signal out of thin air? Well, in a lot of cases, the answer is a clever little circuit called the Colpitts Oscillator. And today, we're going to see exactly how it works from the ground up.
So you look at this and, it doesn't seem like much, does it? It's just a transistor, a couple of capacitors, and an inductor, a few resistors, just a handful of simple parts. So how on earth does this collection of components work together to create a perfectly stable, continuous wave? That's the big question we're going to unravel right now.
All right, here's our game plan. We're going to start with the heartbeat of the circuit. Then we'll look at the big real-world problem it has to overcome. After that, we'll see the elegant solution, dive into the math that makes it all work, and finally, we'll put it all together with a real design example. So let's just jump right in.
Okay, first things first, we need to get to the absolute core of this thing. The entire rhythm, the timing of the whole oscillator comes from one simple, but honestly brilliant little circuit.
This right here is the LC tank circuit. So imagine the capacitor is like a tiny charged-up battery. It's full of electrostatic energy. Then, whoosh, it discharges, dumping all that energy through the inductor, which stores it by creating a magnetic field. But then the inductor's field collapses, pushing the energy right back into the capacitor, charging it up in the opposite direction. It's this constant back and forth, this beautiful dance between electric and magnetic energy that creates a natural oscillation.
And this dance isn't random. It has a very specific tempo, a rhythm, and the speed of that energy sloshing back and forth is set by the values of the inductor, L, and the capacitor, C. This formula right here, that's the mathematical heartbeat of our circuit. It is the single most important equation for setting the oscillator's frequency.
Okay, so that all sounds perfect, right? An endless, perfect oscillation. But there's a catch. In an ideal world, that would go on forever. But in the real world, things are never quite that simple. And we have to deal with a huge engineering problem: energy loss.
And just look at the difference here. On the left, that's the dream. A perfect, beautiful sine wave that goes on forever. On the right, that's reality. With every single cycle, the wave gets a little bit smaller and smaller until it just fizzles out and dies. This decay is called damping, and it's the #1 enemy of any oscillator.
So what gives? Why does this happen? Well, it's because our components aren't perfect. That's it. The copper wire inside the inductor has a tiny bit of resistance. The capacitors might leak a tiny bit of current. So in every single one of those energy exchanges, a little bit of that energy gets lost as heat. If we want to build an oscillator that actually works, we have to find a way to put that lost energy back in.
And that brings us to the really clever part of the whole design. To fight back against that energy loss, we need to give the circuit a little push on every cycle. And we do that using an amplifier and something called a feedback loop.
Here's the genius of it. We use an amplifier, in this case a transistor, to grab a tiny piece of the signal, make it bigger, and then feed it back into the LC tank at just the right time. But for this to work, it has to follow two famous rules called the Barkhausen criterion. Rule 1. The total phase shift around the loop has to be 360 degrees, or 0, same thing. Basically, the push has to be perfectly in sync with the oscillation. Rule 2, the total gain around the loop has to be at least 1. This just means you have to put back at least as much energy as you lost. Simple, right?
Now, the way you build that feedback network is what gives an oscillator its name. For the Colpitts, which is what we're focused on, it's all about using a voltage divider made from two capacitors. Its cousin, the Hartley oscillator, does the exact same thing, but it uses a tapped inductor instead. Same principle, just a different set of tools for the job.
Okay, we've got the concepts down. Now, for all you engineering students out there, it's time to roll up our sleeves and dig into the math. We're going to build the mathematical model that proves exactly why and how this circuit works.
And don't worry, we're going to follow a really clear 4-step plan. We'll start by simplifying the circuit. Then we'll figure out the loop gain equation. And from that one equation, we'll solve for our two magic numbers, the oscillation frequency and the minimum gain we need to make it all work. Let's do it.
So, first things first, to make our lives way easier, we're going to use a classic engineering trick. Instead of thinking about capacitors and inductors directly, we're going to temporarily replace them with these generic black boxes called impedances, Z1, Z2, and Z3. This lets us use standard circuit analysis and just simplifies the heck out of the math at the beginning.
Now remember that first Barkhausen rule about the timing being perfect, the 0-degree phase shift? Well, in the language of complex math, that means the imaginary part of our loop gain equation has to equal 0. So we literally just set that part of the equation to 0, we plug our real components back in for Z1, Z2, and Z3, solve it, and bam, out pops this beautiful formula for the resonant frequency. See? The math directly gives us the answer we were looking for.
All right, on to rule number 2. The gain has to be at least 1. So we take what's left of our equation, the real part, and we solve that. And what we find is amazing. It simplifies down to this incredibly simple condition. The amplifier's gain, AV, has to be greater than or equal to the ratio of C1 over C2. And that makes perfect sense. It's literally telling us that the amplifier's push has to be strong enough to overcome the loss from the capacitive divider. It's a perfect, elegant balance.
Okay, we survived the math. We have our theory, we have our equations. Now for the fun part. Let's put this all together and see how you would actually design a Colpitts oscillator in the real world.
And here you go. This is basically your design cheat sheet. Everything we just spent all that time deriving is boiled down to these key equations. You've got your frequency, your equivalent capacitance, and that all-important condition for the gain. With these tools in your belt, you can design a Colpitts for pretty much any frequency you need. So let's give it a quick try.
Let's walk through a concrete example. Let's say someone hands you this inductor and these two capacitors, and they ask, all right, what frequency is this thing going to produce, and how much gain do I need from my amplifier to make it work?
Well, using our new cheat sheet, this is a piece of cake. Step 1, we find the equivalent capacitance, which is 1.66 nanofarads. Easy. Step 2, we plug that in our inductor value into the main frequency formula, and we get about 27.5 kilohertz. And finally, step 3, we check the gain condition. The ratio of C1 to C2 is 5, so our amplifier just needs a gain slightly bigger than 5 for the oscillations to start up and sustain themselves. Done. It's that straightforward.
So why does all this matter? I mean, why should you care? Because this little circuit is an absolute workhorse of modern electronics. It's hiding inside your phone, helping it tune to different signals. It's the beating heart inside signal generators in every electronics lab on the planet. It is everywhere in the world of high-frequency and RF engineering.
So if you take just one thing away from this whole explainer, let it be this. The Colpitts oscillator is a masterpiece of balance. It takes a natural physical resonance that wants to die out, and it breathes life back into it every single cycle by perfectly injecting just the right amount of energy to keep it going forever. And that's how you create a pure, stable, high-frequency signal. And that leaves us with one final thought. The design itself is a trade-off. If you use a higher gain, the oscillation starts up faster, but the frequency might not be quite as stable. It's a balancing act. And really, isn't that what all of engineering is about? So I'll leave you with this question to think about. Where else do we see these kinds of critical trade-offs defining what's possible in a design? Thanks for joining me.